Today I'll be presenting our effort on deploying actually the first installation of the SlimFly topology. I know this is the first session after lunch, so I'll show you a lot of pictures to make it easy. So yeah, why do we care about this? Firstly, we all know the interconnect is a key part of supercomputers and data centers, which is very relevant for high performance and especially construction cost. Actually, the power consumption can contribute up to 50% of the total power consumption of the data center and contribute up to 1/3 of the entire data center cost. So it's very significant, especially these days. And the big question is, how do we connect these effectively, right? How do we minimize cost and how do we maximize performance, right? What switches do we select, what routers do we select, or endpoints, and also how is the topology designed? And then obviously the follow-up question is, how do we route them, right? If you do not utilize your network effectively, then you're just wasting resources. In this talk, I'm going to touch on all of these aspects a little bit. So the setting is we have a bunch of switches that each connect to the same number of servers, and that are themselves connected in some form of topology via some switch-to-switch links. I'll be using switches and routers interchangeably. This is all built in the InfiniBand setting, where we only use switches. But when it comes to routing, it's a bit synonymous when it comes to Ethernet and InfiniBand. So in the first part, I'm going to talk about what SlimFly is, very, very briefly, to not waste time, and then show how we actually deployed this in practice for the first time at scale. Then at the second part, I'll be talking about routing and how routing changes a little bit in this context of low diameter topologies. And then in the third part, I will show you cool looking plots with some of the data that we collected. Okay, so SlimFly, what is SlimFly? SlimFly is a low diameter topology, which essentially just means that it has at most 2 hops between any endpoint pair. And this is one of the first ones that were proposed back in 2014 with this kind of property of having a diameter lower than 3. And the key idea here is that by lowering the diameter, we basically reducing the average path length, right? And this means we need fewer cables and fewer routers to connect them. How is this actually achieved in practice? Well, let's see here we have a bunch of switches and endpoints that are connected with some topology. And what we do is basically reducing the number of routers and connecting them more densely to the endpoints. So if we have in this example 2 endpoints in red that are communicating with each other, currently that path has a length of hop 3, right? So 3 inter-switch hops that the data needs to traverse. But what we're proposing is essentially reducing the number of routers or switches in the network, connecting them more densely, right? So the endpoints are more densely attached to these switches, and then these switches are themselves connected more densely with each other, which requires hierarchic switches, right? And in this setting, then the path length is reduced to only 2 hops. Now, why do we do this? Well, with a lower diameter, we have higher performance because our packets need to traverse fewer switches, right? So the latency is reduced, but also we have a bit less intuitive lower power consumption because while traversing fewer hops, our packets are stored in fewer buffers, so we need to consume less power, and obviously with fewer switches required, we will have lower construction cost. So let me give you an intuition of the structure of SlimFly. Right, I'm not going to go into the mathematical details, but show you how this looks like from an intuitive point of view. So what we have is 50 routers and 200 servers. The servers are omitted in this picture. And these can be grouped into 2 subgraphs. So each of these switches belongs to one of 2 groups, meaning that, and these groups can be created into 2 subgraphs here on the left and right-hand side, which have identical intergroup connections, right? So they're identical. And there's no wires or connections between groups of the same subgraph. So we have subgraph 0 on the left and subgraph 0 on the right that have the same intergroup wiring connection. And then between these groups, we have a fully connected bipartite graph, right? So there's a lot of connections going from each group of switches in subgraph 0 to subgraph 1 on the right-hand side. As I said, I'm not going to go into the mathematical details of how they're then actually connected. It comes essentially just down to finding a finite field in which you then use these elements to determine the connection algebraically, which results in graphs of diameter 2 at most. So how do we actually take this and put this into practice, right? It looks very complicated, but in essence, it is very simple to construct. and I will show you how we went to this beautiful figure that I spent a lot of time on designing, but how we put this into practice. So we see here, this is 5 racks. I'll go into detail of how these racks are constructed, but it starts off with a lot of cabling effort, right? That goes into this. Okay, so how do we take this physical layout that is the SlimFly and put it into racks and deploy in our data center? Well, the first thing is that we do is we take the subgraph 0 and subgraph 1 and we actually mix these groups pairwise, because this allows us to reduce the intergroup length of these wires, right, of these connections. And the racks follow the same scheme. So by having these pairwise subgroups, we actually just place them into the rack immediately, right? And this will form a fully connected graph between these racks, right? So we have these blue intergroup connections that are now within the rack that were before between the subgroups, right? That were much longer and much shorter now. And then we have the inter-rack connections, which form a fully connected graph here in orange. So how does this look like if we actually now map the single rack to a physical rack? On the right-hand side, we have this picture of one of the 5 racks that we deployed. And you can see very nicely color-coded the subgraph 0 for rack 0 in red, and then subgroup 1 in blue. And you can see at the top we have the switches for subgroup 0 and the switches for subgroup 1 are at the very bottom. And you can see the endpoints are placed in between, right? And then when you want to actually wire this thing, so here's also the color-coded subgroups from the schema that we had before. And if you want to actually deploy this, we can look at this, we do this in 3 steps, right? The first thing is we want to do this very uniform wiring between racks, which I said is the same consistent thing and within each subgroup, right? They're identical, so the top of the rack, this kind of red part, and the blue part at the bottom, always wired consistently across all 5 racks, right? And this is kind of the first step that you do. You can see in the schema on the right, this kind of diagram, these are the intergroup links which do not cross down to the bottom of the rack. It's just the ones between the 5 switches at the top of the rack, right? And the 5 switches at the bottom of the rack, respectively. Then in the second step of wiring the cluster, or a single rack in this case, is actually wiring up this intergroup, right? So between subgroup 0 and subgroup 1, having these copper wires traverse from like the top of the rack to the bottom of the rack, but not between racks at this point, right? So these are what happened by rearranging, by merging them pairwise, these different groups into sets of racks. This is how we shortened the cables and now do not need to rely on long fiber cables in this case. And you can see this here in the diagrams. And then it's the final step for wiring the cluster. Step 3 is we do the intra-rack connections, right, which is this fully connected graph, and for which we used fiber cables, which you can see here in orange. Now, this all still sounds very complicated, right? I didn't really tell you, okay, which ports do I need to connect? Is it as straightforward as connecting a factory? But there's a very effective way of how you can verify this while actually wiring up the cluster. And this is thanks to the algebraic structure of SlimFly itself. So what you do is you essentially assign IDs to all your switches in the cluster, right? Which follow this basically this grid pattern that we have. The first index is the subgroup, and the rest is just the position in the grid, right? And then we can use the actual algebraic structure, which I mentioned earlier is this finite field, whose elements we then use to kind of plug into these the three very simple equations, right, to determine what other switches or routers given switch is connected to, right? These first two determine like the intra-group connections, right? So within a group, how are they connected as the first two, and then the third equation determines how switches or routers are connected between the 2 subgraphs, right? And you can plug this in and combine it with the output of the InfiniBand subnet manager. So while you're deploying the cluster, right, and run the subnet manager on one of the nodes, you can use the InfiniBand tools to essentially query for the current state of the network, right? This will automatically tell you which ports are connected to what other ports and tell you the entire connectivity. And running a simple Python script with this automatically generated design based on this algebraic structure and these ideas, you can get a fully comprehensive report of what connections are still missing, what connections are incorrectly wired, right, and what mistakes or maybe broken wires are in the cluster, right? And that makes deploying this very, very effective and quickly, right, because you can detect errors before you actually start running stuff. But also, generally, with this algebraic structure, I want to show how we did this. Automatically generated these designs, which showed us which port to connect to. And you can see from this diagram that actually the inter-rack connections follow a very simple pattern. The same port in rack 0 is connected to one specific port in rack 1 across all switches, right? So you do not need to verify, okay, everything is going to port 11, because if you have something plugged into port 10, that's obviously wrong, right? So I just want to stress that this is actually a very efficient thing to do and very easy in practice. Now, the next part I want to cover is how do we route them in practice. And for this, I want to start off how routing is done in fat trees, because this is what we're building on top, and this is also, as we'll see in the evaluation, what we compare to, right? And so the key thing is we want to rely on multipathing because this allows us to achieve high performance by spreading our flows across different paths and also avoiding flow collisions. In practice, if we look at this 3-level fat tree, we see that the 2 blue switches want to communicate with each other, and they have 2 shortest paths, or many more as well, but in this case 2 shortest paths that they can leverage to send this flow of data across and thereby increase higher throughput, right, for that flow. Now, this is something that has been done many, many times in practice. There's many different techniques which have been proposed in the past, for instance, ECMP, but also many others. And this is something we also want to leverage in the context of low diameter topologies. Another thing we can do, and that helps with multipathing especially, right, or multipathing is really good for, is breaking flow collisions, right? So in this example that we have at the bottom, you have these bigger circuits which represent switches again, and the smaller ones which are endpoints. And now we have some kind of flow mapping that goes on, right? We have some kind of workload running, and in this very simple case, we do not have any flow collisions, right? The 2 blue endpoints can communicate over the single shortest path that they have, and no collisions appear. However, this is not guaranteed, right? Oftentimes, depending on how we run our workload, we do not have complete control of how we map our ranks and how our data is sent, right? This is where the routing comes into play. And flow collisions are a problem, right? So for instance, in this case, our bandwidth will be halved, right? Because we have a single flow collision. This can be worse, right? We can even have even more flow collisions. And the obvious question is, okay, yes, multipathing will definitely help with this, right? Because we can spread the flow of data across multiple different paths at the same time. However, it doesn't answer yet the question of how many paths do we need in practice, right? And this, thankfully, has been done and evaluated before, and this is part of the Fat Paths paper that was published in 2020, where they found that for most common and traffic patterns, it is actually sufficient to have 3 disjoint paths. What does that mean? Well, between any router pair, if we have 3 disjoint paths, that means 3 paths that we can leverage to send traffic on that will not have any intersecting links between them, we will be able to alleviate any kind of flow collisions, right, and avoid congestion that way. So it's clear what we want, right? We want 3 disjoint paths, shortest paths ideally, in order to alleviate all the flow collisions. But how does this work in practice on SlimFly? And the answer is no. Why? Because for most low diameter topologies, there's almost only a single shortest path. Meaning that if I do minimal path routing, or like multiple, like ECMP for instance, there will only be a shortest path, so everything will be sent along that shortest path. So what we need to do in practice is we need to use this idea of almost shortest or almost minimal paths, which basically just means 1 hop longer than shortest. So in the case of SlimFly, where we have a diameter 2 topology, so the longest path is 2 hops, we say, okay, it's okay to use paths of length 3. Right? So we go 1 hop longer. And how do we find this? Well, FatPath proposed this idea of creating layers, and this was for the Ethernet stack, right? And it's basically each layer is a copy of the original layer, but then we randomly sample edges in that layer, right? It's basically just a random sample, which is acyclic, very important, otherwise you result in deadlocks on Ethernet. And then within each layer, you route minimally, right? And that way, by having sufficient number of layers, you will generate a set of paths which hopefully contain 3 disjoint paths, right? And then you spread and load balance your traffic across all these different layers. However, what we find in practice is that you need a huge number of layers to actually achieve these 3 disjoint paths, right? Because by randomly just sampling different edges, this is not very efficient. But this comes down to, and what happens in practice is you have a lot of link overlap that way, right? You see that these, yes, you have two non-minimal paths, but they still share an edge, so they are not disjoint. So there you will have flow collisions in that case. Now, in practice, what we want is clear. However, the cyclicity requirement for Ethernet kind of puts us in a bad position, right? Because we don't know how many path layers we need, and in practice, we need too many. But we are in the InfiniBand setting. And I need to skip about this a bit quicker because I only have 3 minutes left, roughly. But what we do is we kind of break this constraint and hand this deadlock resolvence off to a different level, because in InfiniBand, we can rely on service levels to kind of create virtual links. In the end, what matters is we can explicitly select paths that minimize the overlap that we have, right? So in this case, we need fewer layers to generate a much better sample of paths that have a higher probability or higher chance of having fewer flow collisions and these 3 disjoint paths that we want. And this is how the kind of routing that we propose in this work as well. Now, I want to finish off with the actual evaluation of our system, right? Because we run a huge amount of benchmarks when it comes to deep learning, proxy workloads, scientific simulations, as well as HPC benchmarks. So there's something for everyone. And for a baseline, what we actually did is we set up using the same hardware, we set up a 2-level factory, a non-blocking 2-level factory, and run the same set of benchmarks to use as a baseline to compare the performance of SlimFly to. Because SlimFly is, in theory, non-blocking, right? But we wanted to show this in practice as well. And for placement strategies, we linear placement for both SlimFly and factory. And for routing, for these benchmarks, we relied on DFSSP for SlimFly and standard multipath factory routing for the factory. DFSSP is just the same idea, multiple shortest paths, right? Which in theory, as we just discussed, has this issue where you almost have only a single shortest path available, where our new routing should help. Now, we run a lot of things. I will focus only on a few benchmarks. So in this case, the micro benchmarks here, I'm showing is broadcast and O-reduce, where we're essentially just plotting the relative performance of SlimFly to factory, right? So if it's the peak performance achieved of SlimFly divided by the peak performance achieved on the factory for the same setting. And we can see that for like fewer node counts, that is 8 to 16 nodes and fewer, the factory seems to have a marginal advantage. The reason for this is very simple, because behind a single leaf switch on the factory, there's 16 nodes, right? So with linear placement, there's a 0-hop communication between these 16 nodes. So especially for smaller message sizes where we are very much latency bound, this will be much more efficient compared to the setting, or much more marginally more efficient than on the SlimFly where we only have 4 nodes being edge switched. Okay, and I'm going to finish with the all-to-all, where we have high traffic congestion, but this is only because we did not have adaptive load balancing on our system, because this was fairly old hardware. But by using a different placement strategy on SlimFly, we actually outperform the factory quite significantly in these situations. Okay, and unfortunately I don't have more time, but we also run cool deep learning proxy workloads, which is essentially the forward and backward paths, where we can see the same effects of having lower number of nodes result in marginally worse performance because of locality, but then on the higher switch cost with GPT-3 with a lot of data that is being reduced, we can see that we have higher performance again, which matches the performance on the micro benchmarks. Okay, and yeah, our routing does also improve in these situations where we expect a lot of congestion on the single shortest path. Thank you. And yeah, if you have I hope you have many questions, but there's a lot more details and benchmarks in the paper, which I hope you can check out afterwards as well. Thank you.